Hello, and I would like to record another high peak education video where I am examining centripetal force and in fact non-uniform circular motion. And this non-uniform circular motion problem will involve Tarzan and will be a vertical circle where gravity enters the picture so that it is non-uniform circular motion. So let us have a look at this example. Tarzan, who has a mass of 85.0 kilograms, tries to cross a river by swinging on a vine. The vine is 10.0 meters long and his speed at the bottom of the swing is 8.00 meters per second. The vine has a braking strength of 1,000 newtons. A. Does he make it across the river? And B. How fast must he swing to do a full inverted loop? Okay, well, let's go ahead and start this problem by writing down our knowns. So we'll start with that the mass is 85.0 kilograms. And we also know that the length of the vine, okay, is going to be 10.0 meters. And we know that V at the bottom is equal to 8.00 meters per second. That's the velocity. And we want to know, does he make it across the river? And we also know the vine has a braking strength of 1,000 newtons. So I think that's going to be the tension force. So tension force maximum, you could say, is equal to 1,000 newtons. And furthermore, when we think about the length, I think that the length will essentially be the radius. And let's see if we can understand that by drawing a picture. Let's assume this is the top of the forest canopy, say right about here. And this is just a sketch. And Tarzan's coming down. So this is, this is Tarzan at the bottom here. Okay. And we can just model Tarzan as a particle. So Tarzan's going to have some path like so. And we know that this is the length, but this should also be the radius from some axis of rotation. And then here is Tarzan himself. Okay. So you can imagine that, this is effectively going to act as a radius when we have the length of the vine. Okay. So we want to figure out what essentially is the tension at the bottom of the swing, because we want to know if he makes it across the river, whether the cord, that is the vine, snaps or not. So what is Ft bottom? Well, we can essentially use what we've got here in terms of the picture, but we should draw a free body diagram. So let's say that if this is the particle Tarzan, then we can imagine that the tension force is upward, okay? But we know that Tarzan is in circular motion. Now, he's not in uniform circular motion. He's in non-uniform circular motion. In fact, one way to think about this is gravity was giving a positive force, like an mg sine theta, theta being the angle that the vine is at, in the direction that Tarzan's going during his vertical circle, so that essentially Tarzan is accelerating downward, so his velocity is increasing, so his centripetal force should be increasing. Now, since he has a centripetal force, he's in non-uniform circular motion, but there is a centripetal force. I think that the tension force, that's this, or this, should be larger than his weight, because I think that his weight is also another vector we should consider. Okay, so like so. Okay, so there's mg, his weight, and let's call upward the positive y direction. Okay, so let's call this the positive y direction. Okay, and we can write down Newton's second law in the y direction. The sum of the forces in the y direction should equal the tension force minus the weight And that should equal to not just any force, or not just any acceleration, mass times centripetal acceleration. And by the way, immediately you could have written mv squared divided by r. Okay? So let me fill in the other forces. I need the other colored pens. So tension force minus weight, mg, should be mass times centripetal acceleration, which is mv squared over r. Now, by the way, this v is actually the, what do you call it? The v at the bottom. We actually know what v at the bottom is. So we can find the tension force required at the bottom. So this is the tension force at the bottom, just what we've got labeled here. All right, so we should be able to solve for that tension force at the bottom by adding the mg over. Okay, so I'll just do that over here. And by the way, I'm just going to do the algebra here in black. So we'll have, let's see, the tension force at the bottom that's required to maintain this circular motion is equal to, or at least it's part of a circle. Let's see, that's going to equal to mg plus mv squared over r. So the weight plus the centripetal force. So let us put the numerical values in. This is 85. Sorry, that's an 85.0 kilograms. And g we know to be 9.8 meters per second squared. We assume that is constant near the surface of the Earth. Plus mv squared, so this is 85.0 kilograms times v squared, that's 8.00 meters per second, and we square that, and we divide by the radius of 10.0 meters. Okay, so let's go ahead and get this F T at the bottom. Okay, let's move this away to not distract us. And let's go ahead and get the calculator out. So we've got, let's see here. So I'll be adding to, let me turn it on actually. I'll be adding to, sorry, a fraction stack. So why don't I do 85, I don't need the significant digits in the calculator, times 9.8, plus, then I'll do alpha, this y equals gives me f1. I need this, I want this n over d, this fraction stack. And then I should have 85 times 8 squared, and I'll divide that by 10. Okay, so let us write this down. That's about 1,380 or so to 3 significant digits, newtons. Now that Ft at the bottom should be greater than the Ft max. So the maximum breaking strength of the vine. So this tension force is too large, so the answer is no. He does not make it across the river. So we would say the vine breaks. And we found that because based upon the velocity, we know that, essentially Tarzan would have too fast of a velocity, thus too large of a centripetal force added to his weight. And keep in mind, this centripetal force is the net force. Don't think of the centripetal force as some additional force. It's the new way to write the net force. So he needs a very large net force given he's going so fast. In other words, he needs a much larger tension force than the weight in order to achieve that circular arc. Okay, how about B? How fast must he swing to do a full inverted loop? So for part B, let's start off with this. Let's assume, if he's going to do a full inverted loop, assume the vine does not break. Okay. Also, we're going to allow Tarzan to swing to the very top. Okay? So in other words, just a little sketch will give us something like this. He'll be, instead of swinging just here, he's going to go all the way barely to the top. So when we're talking about the velocity, that is the velocity of Tarzan at the top, and this you can imagine as the vine, what we're really saying is he can't have zero velocity at the top, because if he loses his velocity on the way upward, in other words, there's a negative force of gravity in the direction of motion, or you could say that gravity is doing negative work. If he gets to zero velocity at the top, he won't actually make it through the loop. Turns out that if his velocity was zero, he would just fall right there. So he needs to have a non-zero velocity. So what we're looking for is v at the top. So we want to know what the velocity at the top is. Okay, so we'll go on to the new board and then we'll see how that works. Okay, now that we're on this new board and we're looking at Tarzan's velocity at the top, let's go ahead and just sketch that. So here's Tarzan, here is the chord. So you can imagine that, again, this is the radius, but now the forces are in a different direction than what we had before, at least the tension forces. Because I believe that the tension force is this way, but it's kind of small, and the weight has not changed from what we did before. That's still in the same direction. So this is mg. Okay. So now that we have the tension force and the weight in the same direction, let's now call the radial direction, that is the direction of interest, inward. So usually radial axes are defined as inward toward the center of the circle. Okay? So there we go. Now, if that's the radial direction, in this case, it's going to be tension force plus mg equals mv squared over r. Because notice that the tension force and the weight both contribute to the centripetal force. So let us add these two force vectors in the radial direction, and that's going to be mv squared over r, the centripetal force. Remember, this is the net force, but this is now v top. And we have the tension force and the weight, are both in the same direction. Now everything looks good. So, let's also say, what should the tension force be? That was not given to us at the top here. Whoops. Let's do this in red because it's the color that we're looking at. Top. So what should the tension force be? Now, if Tarzan barely makes this loop, you can imagine that the chord has just a little bit of tightness as you go up, but it should be just about zero when it gets to the top of the loop. If that's the minimum speed that he can go to barely allow him to make it through this loop. So you could imagine that F T top is approximately 0 newtons. Okay, so let's just put a 0 in here at the top. So then mg equals mv squared over r. And the masses then would cancel. Notice that we can get v top is equal to g times r and the square root. Okay, so that should be the velocity at the top. By the way, many of these velocities that have to do with vertical circles and have to do with gravity have kind of this gr or gr tan theta business going on if there's an angle. But in this case, there's no angle really to speak of. So we just need the square root of 9.8. So 9.8, sorry, meters per second squared times the radius. And we still know that that's 10 meters from the previous board. So we only need the square root of 98 bring the calculator back. We just need the square root of 98. Second square root. Whoops. Need to turn the calculator on. Square root of 98. So it's about 9.90 approximately. So we'll write that down. That's approximately 9.90 meters per second. So that's going to be Tarzan's minimum speed at the top because, again, it's not going to be 0 at the top because he has to sort of make it through the loop. He has to not fall out of the cord there. But the cord, that is the vine tension, can be non-zero as he approaches and non-zero as he goes away. And it can be small, but it can be 0 just for this moment here, so that that's going to be his minimum speed through the top to make this vertical circular loop. So this is a centripetal force problem for non-uniform circular motion. So thank you very much for your attention. This was part B. Okay. So I appreciate you watching High Peak Education. Please smash that like button if you enjoy this content. Please share this with your social network. And please subscribe to the channel in order to grow the channel. I will see you in the next video.